Okay, so we will start the class now. Okay, so first, can anyone confirm that what is was
So
uh,
lecture number 4, chapter 10, vapor power cycles.
okay, thank you. So we will start with the again chapter number 10. Okay, so previously we already see different topics related to vapor power cycle. Okay, so we already go through Rankine cycle. Okay, and I hope all of you know that what is the Rankine cycle now. Okay, so then we will deal with the ideal case also. Okay, so we already see ideal one. We already know how to deal with the actual Rankine cycle also. Then we already see the reheat one. Okay, how to uh, increase the efficiency of your turbine of your vapor power cycle by using the reheating process. Okay, so then we will also we already look for that how we can decrease the pressure of condenser, okay, to achieve the maximum work output, work for your cycle. How we increase the boiler pressure, okay, then how what is the effect of the increase of boiler pressure on the efficiency. Then we already uh, discussed in the previous class how the superheating of your steam will contribute in order to increase your so this is your steam one, contribute towards the increase in efficiency. So in this class, it is also similar to the vapor power cycle, but here previously we deal with the ideal reheat cycle. Okay, and in this class we will look for the actual one, actual reheat cycle. Okay, so we will see that how to thermodynamically analyze the actual reheat cycle when there will be a irreversibilities in the system. So just a quick Rivian, okay, that what is the difference between the actual and ideal one? So we already know that the actual power cycle and the ideal Rankine cycle, the difference come from the irreversibilities, and these irreversibilities will be in the form of many factors. Okay, so the bus, but most importantly, it comes from the fluid friction. Okay, so fluid friction causes some pressure drop in your piping components in your processes where there will be a boiler installed, there will be a condenser installed, or it might be in the turbine section as well. Okay, so these fluid friction can cause and decrease in efficiency of your whole cycle. Okay, and then there will be irreversibilities due to these fluid friction. Then the second cause of irreversibility is heat losses. So definitely when we are dealing with the actual one, it is not possible to convert all the heat which you have supplied to your work. Okay, so definitely there will be some loss of energy in your actual cycle, but in the ideal case we assume that there will be a no uh, heat losses, so that's why we get the maximum efficiency from the ideal case. Okay, so this is just a revision. Okay, and then we already see the TS diagram because we will also use the same TS and diagram in order to discuss the actual reheat cycle as well. Okay, so we already know that 1 to 2 we have for the actual case there will be an increase in entropy. Okay, so that's why there will be a deflection towards the right side. Then there will be a decrease in boiler pressure. Okay, so that's why this line is shown to continuous line, which is in this diagram. Then there will be a 3 to 4, also there will be an increase in entropy, okay, at the exit of your turbine. So that's why this 4 point is shifted towards this side. Okay, so then coming towards, we already know that if it is isentropic, then we have to deal with the points 2s and 1, okay, for the pump section. And if there will be turbine, then we have to deal with the 3 and 4, but there will be a isentropic process 4s and 4a. Okay, so coming towards the relation, we already know that what is the meaning of this relation, that this is the isentropic work for your pump, and then there will be actual work for your pump, and then we can define the isentropic efficiency of the pump because we use the similar relation in the analysis of reheat cycle as well. Okay, so then similar for the turbine section, isentropic efficiency of the turbine, you have to divide actual work, which is your S3 minus H4A, and your isentropic work for this one. Okay, so I hope that you all are clear that why this WS term is above and this WA is below, and this WA is above and this WS is denominator. Okay, so I already explained in the previous class as well. Okay, so now coming towards the actual reheat cycle. So we will start with the one example. Okay, so if you can just read the example first. Okay, and one thing that you have to make sure that after all the classes, you have to practice these questions by yourself, because if you cannot practice, you cannot find the enthalpy within the time during your exam session as well. So going towards the problem statement, consider a steam power plant. Okay, so there is a steam power plant. It's mean that it is working on the vapor power cycle that operates on a reheat Rankine cycle. Okay, so it is mentioned that there will be a reheating in this cycle, and the network output is 80 megawatt. Okay, so your power of your total power is given in the problem statement. So steam enters the high pressure turbine at 10 megapascal and 500 degrees Celsius, and the low pressure turbine at 1 megapascal and 500 degrees Celsius. It means your pressure at point number 3 is given in the question. Temperature at point number 3 is also given in the question, because this is a high pressure turbine. So it is mentioned that high pressure turbine, the pressure and temperature is this. The low pressure turbine at 1 megapascal. Okay, so at low pressure, it's mean that your P5 is given. Okay, and then your T5 is also the same as of T3, because it is same 500 degrees C. Then it is mentioned that steam leave the condenser as a saturated liquid at a pressure of 10 kilopascal. It's mean your this pressure is given in the question. The isentropic efficiency of the turbine is 80%. So because there are irreversibilities in the system, so it is you have to judge from this statement when there will be isentropic efficiency of the turbine is 80%. So it's mean that there are irreversibilities. So this is the actual Rankine cycle. If this statement is not available in your question, it's mean it is on the ideal one, or either it is mentioned in your question that it is an ideal reheat Rankine cycle, and if it is not mentioned that the isentropic efficiency of the turbine is this one, then you have to assume that this is the ideal reheat Rankine cycle. Okay, so it is mentioned that the turbine is 80% and the pump is 95%. So it's mean that isentropic efficiency of the pump is also given in the question, and isentropic efficiency of turbine is also given in the question. So it says that show the cycle on the TS diagram. You have to develop the TS diagram for this cycle, which is already shown in this slide, and then the quality of the steam at the turbine exit. So you have to find X, which is the quality. You have to find thermal efficiency of the whole cycle, and you have to find the mass flow rate of the steam. So we already know that we have to find enthalpy on all the points. Either it will be isentropic one, or either it will be actual one. So then we can find the thermal efficiency of whole cycle. So now coming towards how to analyze it. Okay, so it start with the same process which we already see on the analysis of the Rankine cycle. So because the pressure at the condenser is given, okay, which is 10 kilopascal, so we will start from point 1. Okay, so at the point 1 we just have to go to saturated water table. Okay, and we can look for the pressure one. Okay, and we will find the value 191.81 by using 10 kilopascal pressure. The similar thing for your specific volume as well. So we have to go to thermodynamic table and find the value. Okay, so now coming towards the pump work. Okay, so as we already know that the isentropic efficiency of the pump is given, so it's mean that we have to find the actual pump work, okay, rather than isentropic one. Previously, in the previous question, when there will be a no irreversibility, then we only find the isentropic pump work. So here we already know specific volume into P2 minus P1 is the relation, and right now we have to divide the isentropic efficiency of the pump in order to find the actual pump work. So this come from your state 1. This is given in the question. Okay, 10 megapascal, 10 kilopascal is also given in the question. Okay, so just plug in all the value, and 0.95 is also given in your question that your isentropic efficiency of the pump is this one. Okay, so now just solve it, and then you can get the actual pump work. Now coming towards the H2. Okay, so this is H2A, which is actual one. Okay, so there will be two H2S. So we have to find the actual enthalpy, because we need to find the actual enthalpy at all the stages. So this is our main objective, because we have to plug the value in the thermal efficiency equation for the actual one, not for the isentropic one. So H1 we've already find from state 1. Okay, so this come from your table. This you already find in the previous state, and then you can plug in all the value and you can find the H2A value by using this relation. So now coming towards state number 3. Okay, so state number 3 is this one. So we already know that it is a superheated one, superheated state. Okay, so you have to go to superheated table. And for superheated table, you need two values. Either it will be a pressure or temperature. So you can easily find the value of enthalpy for state number 3 by using the table, and you can get the S3 and S3. Now, another important thing is that the point number 3 to 4 is your isentropic mean. Your S3 is equal to S4. It is an isentropic process for your 4S. Okay, but for 4, which is the 4A, it is not an isentropic process. So we will see that how to find the 4A and 4S as well. So 4S, again, it you already know 1 megapascal is given in the question. Okay, so because P5 is given, so P5 is equal to P4, and S4 is equal to S3, mean that our second value, which is 6.5995, is also given from the previous step. So now the question here is that how to find H4S. So again, we have to use the interpolation. Okay, we already know how to do the interpolation, but we will quickly see how we can perform the interpolation for this one. So first you have to note the value of 6.5995 on your notebook, and P4S is 1 megapascal, because we have to use these value in order to find the enthalpy at state number 4S. Okay, so now coming towards the interpolation term, that how we have find the values. Okay, so now you have to open your thermodynamic table. You have to find out the superheated one. So just go to superheated tables. Okay, so this is your superheated water table. Okay, so now you have to find the pressure 4S is, which is equal to 1 megapascal. So we have to look for 1 megapascal in this table. 1 megapascal is this one. Okay, so for 1 megapascal, we already know that what is the value of so we already know that our entropy at point number 4 is 6.5995. Okay, so we already captured this one, okay, previously from point number 3. Okay, so now we have to judge it that where this 6.5995 lies on this uh, P is equal to 1 megapascal superheated table. Okay, so if we can just notice that 6.6 956, okay, and 6.5850. It's mean that our value 6.5995 lies in between this value and this value. So these are our 2 points where we have to look start from the interpolation. Okay, so similarly we also know that at number point 1 it is 277.1 or enthalpy, and 28.3. So we have to find the enthalpy in between these state. Okay, so now we have to start with the interpolation. We already because it comes from your mathematics, so we already know how to do the interpolation. So the H which we have to find, which is in between this 777.1 and 2828, which is unknown to us. What is the value of this? We have to find it. Okay, so the initial value, which is 277.1. Okay, so this you have to go in the previous lecture. You can easily find that how to do the interpolation. Is 6.5995, which is from state number 3. Okay, so state number 3 and state number 4 entropy is constant. Okay, and then 6.5850, which is from your initial point. So it is written over there 6.850, which is equal to 28.3. So this is the enthalpy at your this point, 28.3 minus 2,777.1 at state number 1, and then 6.6956 minus 6.5850. Okay, so now you just have to solve this. Okay, and you can easily get your entropy enthalpy value. H is equal to, you can just solve by using calculator, 2783.81. Okay, so this is your value of enthalpy at state number 4. Okay, so a similar thing is available in your slides as well, that this is how we can find the enthalpy at state number 4S by using the interpolation. I hope you all know how to do the interpolation, because you can use frequently in all the questions which will be coming in the next lectures as well. So I will suggest you have to practice this thing, that how to do the interpolation. Okay, so now coming towards H4, because we are interested in enthalpies for the actual one. Okay, so we have to find the H4 by using the isentropic efficiency of the turbine equation, which we already see that how to find the isentropic efficiency of turbine. H3 minus H4A, this is H4A. Okay, H3 minus H4S. Okay, so you already know that H3 value from your previous state. H3 is given, H4S you have just find by using the interpolation. So you just plug in all the value. This is given in your question, because isentropic efficiency of turbine is equal to isentropic efficiency of the pump. So that's why we have to use the same value for the turbine as well. Okay, so plug in all the value, you will easily find the value for H4A. Okay, so from the state 4A, we find the enthalpy. So now coming to state number 5, we already know the state number 5 is also in the superheated region, and the pressure 5 is equal to pressure 4. So we know the pressure number 5, and temperature 5 is also given in the question, which is 500 degrees Celsius. So again, you have to just follow the superheated table, and you can easily find with the pressure and temperature data for the enthalpy also, and your entropy as well, which is 7.7642 by using the superheated table. Okay, so now coming towards 6S and 6A. So we have to find the 6S also and 6A as well. So P6S, we already know that it is 10 kilopascal, and entropy is constant for your S5 state. So S5 is already you already find in the previous state. So just plug in the value in this equation, which you already know that how to find the quality. So you can easily find the quality by plug in all the value by using the, and these value you can find with the 10 kilopascal for the pressure table using the water pressure table, and you can easily find the quality as well. Now coming towards H6S, which we have to find the enthalpy at 6S. Again, using the same equation, you can use put all the value. This is given from your previous state. This you can find from table uh, by using the 10 kilopascal data, and you can plug in all the value. You can find the H6S also easily. Okay, so there will be a no difficulty till this point. Now coming towards your state number 6A. Okay, so again 6A, you have to use the okay, another point over there, because in the question it is mentioned that your turbine efficiency, isentropic efficiency of the turbine is how much it is mentioned. So we'll see that it is 80%. Okay, so it is mentioned that isentropic efficiency of your turbine is 80%, but it is not mentioned either it will be a low pressure turbine efficiency or either it will be a high pressure turbine efficiency. So when it was not given in the question, it means that isentropic efficiency of both of the turbine is 80%. So you have to use isentropic efficiency of this turbine as well and this turbine as well as an 80%. But if it is mentioned in the question that the isentropic efficiency of your first turbine is 80% and second turbine is 90% or some other value, so then you have to plug that value on this equation. So again, you have to apply isentropic efficiency for the relation for your turbine, which is installed between 5 to 6. So H5, H6A, which we have to find, H5 and H6S. So this you have to find. This is available from your previous data, which is over there. Okay, this is given in the question. This you already find in the previous state by using the pressure at 10 kilopascal. So just plug in all the value and you can easily find the enthalpy value. So now another important point over there is, because at the point number H6, you do not know either it will be a superheated vapor or either it will be a saturated vapor. So because you have to find the properties for a temperature as well at point number 6. So how to find the temperature? So first you have to judge it by using your thermodynamics 1 analysis, that you already know that if your enthalpy is greater than enthalpy at your gaseous state, it's mean it will be a superheated region. It will be a superheated. Same for if your specific volume is greater than specific volume at G. so then it is also a superheated one. Okay, so this is one check from which you have to just analyze that either it will be a superheated vapor or it is not. Okay, so if you do not know how these relation come from, you have to go to chapter number 3 for your thermodynamics 1 course and revise the pure substance. It is mentioned in that chapter also. Okay, so once we know that this value is greater than uh, your gaseous one, so then we know that it will be a superheated vapor. Okay, so now coming towards the question that how we can find the temperature at 6. Okay, because we already know that the temperature is 10 kilopascal, mean it will be lies in the superheated region. So we have to just go to thermodynamic table, and again we have to apply some sort of. Okay, so before going to thermodynamics table, you have to just note down somewhere your value of enthalpy at state number 6a, 2664.8. Okay, so this you have to follow, and pressure 10 kilopascal, you have to note it down. Okay, so now we have to move towards our, again you have to do the interpolation. Okay, so we will see how to do the interpolation for this case. Okay, so this is your thermodynamic table for your. Okay, so what we have to do is we have to just go to 10 kilopascal. Okay, so and it is a superheated one. So if you can notice that this is mentioned P is equal to 0.01 megapascal, and when you convert into the kilopascal, it will turn into 10 kilopascal. Okay, 0.01 megapascal you can just convert to kilopascal, you will get 10 kilopascal. Okay, so once we notice that this is our pressure range, okay, and we have to find value out of this area. Okay, so we already know that the enthalpy value is 2664.8. Okay, so now you can just look for the enthalpy value in this line where the 2664.8 lies. Okay, so if I can notice that it is in between these 2 points. Okay, so 2592.0 or 2687.5, the value of 2664.8 exists. Okay, once we know that the existence of your enthalpy value is in between, okay, so then we can easily apply the interpolation, because we already know the temperature on this one and we are looking for the temperature term. So we mean we already judge from this data that the temperature is for the T6 value is between 50 to 100. Okay, so once we know, we can just simply go for the interpolation. So for the interpolation mean that you have to find the temperature in which you are interested in. So initial temperature is 50. So just look for this. You can just 51. Okay, and then 50, after 50 you can just plug the enthalpy value which is in the denominator. This is your enthalpy value come from your state number at 6a. Okay, so just 2.5 2592.0, which come from this one 2592.0. Okay, so then again you have to just plug all the value in the interpolation term. So it comes 100 minus 100 is your final temperature, 50 is your initial one, 2687.5. Okay, so this 2687.5 come from this, and then minus 2592.0. Okay, so just solve for your temperature. You can easily find the temperature which is equal to 88.1 degree Celsius for the state number 6. Okay, so for state number 6 you can find the temperature in this way. So this is where it is mentioned that your temperature at 6 is 88.1 degrees Celsius. Okay, by using the interpolation. So that's why I'm suggesting that you have to just go through the interpolation quickly. Okay, so now coming towards our main question, we have to find the enthalpy. We have to find the thermal efficiency. Okay, we already find the enthalpies at all the stages. Okay, so we need the W net and Q in order to find the thermal efficiency of our whole actual reheat Rankine cycle. So we need first turbine out, which is your work for your turbine. Okay, so there are two turbines installed in it. So we need to add both the turbine for your turbine first and your turbine second work. Okay, so these are the two turbines. So we already know that turbine 1 is installed between 3 to 4 and turbine 2 is installed between 5 to 6. Okay, so we need the enthalpy value at H3, which is available. And one thing you have to remember, whenever you are dealing with the actual one, you have to use actual enthalpy value, okay, rather than you have to use the isentropic one in the case of ideal one. Okay, so make sure that you have to just plug all the value which is the actual enthalpy value. Okay, so you already know all the enthalpy value you already find from the enthalpy one, and 1287.4 kilojoule per kg you can easily find the turbine work. Okay, so now coming towards the second thing, we have to find the Q supplied in the boiler also. We already know that there will be a two heat addition process. So because it is a reheating one, so there will be a one heating process between 3 to 2 and one heating process between 5 to 4. So we need an enthalpy of 3, enthalpy of 2, 5 and 4, and all of them are the actual one. So you already find the actual enthalpy previously. Just plug in all the value, you will get the enthalpy, the Q in, which is the Q supply to your boiler. So now coming towards your W net. Okay, so W net is equal to turbine out minus, which is your actual pump work. Okay, so then you have to plug in, because you already find all these things, you can easily find your W net by using this relation. When you already know these value, you can easily find the thermal efficiency for your whole actual reheat Rankine cycle. That's come to be 34.1%. So similarly, the C part, which is mentioned that you have to find the mass flow rate of the steam as well, and this you have to find by using the power which is available in your question, that it is a 80 megawatt of your power plant, and 1276.9 you just find from your this knowledge W net, and you can easily find the mass flow rate as well. Okay, so this is how you can deal with the actual reheat Rankine cycle. Okay, and I hope it will be not a difficult one, because it is using the same knowledge which is we already see in the previous cases as well. Okay, so if there will be any question, you can ask me. Okay, so I hope there will be no question, because after this you have to do one question by yourself. Okay, so we will see that which question you have to attempt by yourself. Okay, so you have to read this question first. What you have to do is, because this is the same question which we already discussed previously, just there will be some data which is different from the previous one. You have to reply to me with your ID, with your section. Okay, and you have to upload the picture of your work. Okay, so you have to just write down all the things in your notes, and you have to just take the picture and upload on the my inbox. Okay, because previously I see that most of the students, I think, just copy the final values which is thermal efficiency and just inbox me. I think they will not doing the calculation by themselves. So I will suggest you have to just upload the picture rather than you have to mention the just thermal efficiency values as well. So now we have to read the question first. A steam power plant operate on the reheat Rankine cycle. So first we already know that it is a reheat Rankine cycle. Steam enter the high pressure turbine. So we know that over P3. So this is your high pressure turbine, and 550 degrees Celsius. Temperature is also given at 3 at a rate of 7.71 kilogram per second. So mass flow rate is also given over there. Previously we have to find the mass flow rate in the previous question, and leaves at 2 megapascal. So it's mean P4 is also given, which is 2 megapascal. Okay, so steam is then reheated at a constant pressure to 450 before it expand. So it's mean our temperature is also given at this rate, which is 450. Okay, so before it expand to the in the lower pressure turbine, steam leave the condenser at a pressure of 20 kilopascal. It's mean that condenser pressure is at P6 and P1 is given to you, which is 20 kilopascal. Okay, so now from there you can analyze, you can also judge easily that the isentropic efficiency of the turbine and the pump are 85% and 90%. So it's mean it is working on an actual reheat Rankine cycle. Okay, so it is not an ideal reheat Rankine cycle respectively, and steam leaves the condenser as a saturated liquid. If the moisture content of the steam at the exit of the turbine is not exceed 5%, it means your quality is also given. Determine the condenser pressure. Okay, so you have to find the condenser pressure, and then the net power output and the thermal efficiency. Okay, so you have to find these value by using this data. So you can note down this question, and if you have any question related to this problem statement, you can ask me.
सर बस ये ABC के आंसर से आपको सबमिट कराने हैं ना?
जी आपने बस लेकिन अपनी जो बुक पे नोटबुक पे आप लिखेंगे ना बाय हैंड, उसकी पिक्चर आपने मुझे सेंड करनी है. ओके, सो यू डू नॉट नीड टू राइट ऑन द इनबॉक्स. ओके, सो जस्ट हैव टू अपलोड द पिक्चर. You can take your mobile, take the picture of your work, and you can just upload it.
ओके सर.
And one thing you have to make sure that you all have to practice by yourself. Do not need to copy with the other students, because in the paper you cannot see the question similar in this pattern. You will see the difficulty level of the question in your sessional exams are way more high than this one. Okay, so if you do not know how to find the enthalpy's value and all this stuff, you cannot solve the question easily. Okay, so I hope you all have noted down the question. So if you have any question, you can ask me on my inbox as well. I can reply over there also. So I will just stop the presentation.